All right, here we go. This is problem number 60 from Chapter 6 of the Holiday and Resnick textbook on your worksheet. This is on assignment 6.1b. All right, so here we go. We've got a box of ants, ants, and a box of ant uncles. All right, so here's what we know. Box 1. Box 1. Here's what we know. We know that our mass is 1.65 kilograms. We know that for box 2, mass of box 2 is 3.30 kilograms. Useful to note that that is exactly twice the mass of box number 1. Let's see, and it slides down. You've got this rod attaching them here. So here's our rod. It tells us that the angle of the incline is 30 degrees. So let's take a second and do this. We know that our force of gravity over here for rod 1 is going to be 16.17 newtons, which means that the force of gravity number 1 parallel is going to be 8.085 newtons. And our FG1 perpendicular is going to be, turns out, really close to 14.00 newtons. All right, and our force of kinetic friction on number 1, because in a minute here it's going to give us our coefficients of friction, right? So let's write that down. Mu K on box 1 is 0.226, and the coefficient of kinetic friction on box 2 is 0.113, so half of the coefficient. So our force of kinetic friction on box 1, just by taking this coefficient and multiplying it by our normal force, right? Because our normal force has to equal our perpendicular component. So that turns out to be 3.1648 newtons. All right, let's go over here and do some similar calculations. The force of gravity on box number 2 is twice as big. So that gives you 32.34 newtons. FG2 parallel, the parallel component there turns out to be 16.17 newtons. Our FG2 perpendicular ends up being 28 newtons. That's going to be the same as our normal force on box number 2. And the force of friction kinetic on box number 2 also turns out to be 3.1648 newtons, because you've got twice the normal force but half the coefficient of friction. Okay, so we haven't even really done anything yet except to sort of do some preliminary work. All right, so let's take all this stuff. We're going to need all of this, and let's kind of free up some space on the board. All right. All right, so we've cleaned up our space a little bit here. All right, so what we're trying to do is we're trying to find the tension in the rod. All right, so the first thing that I want to do is I want to find, in general, when you're doing a problem like this, the first thing you want to do is look at the system. So my system here includes mass number 1, mass number 2, and the rod. All right, so let's see if we can figure out what forces are acting on this. All right, so first of all, we're going to have 2 parallel components of gravity. Remember, we're looking at the whole system. All right, so everything that I'm about to draw here is pertinent for the whole system. All right, so we're going to have 2 parallel components of gravity. We're going to have the force of gravity on number 2 parallel, and we're going to have the force of gravity on number 1 parallel. So according to my calculations over here, let's see, number 1 was, let's call this negative 8.085 newtons. And on number 2, it's negative 16.17 newtons, right? Now we've also got friction affecting this thing. So we're going to have the force of friction kinetic on number 1. This word is in my way, so I'm going to just get rid of it. So that force of kinetic friction is 3.1648. And we're also going to have the force of friction kinetic on number 2, which also happens to be 3.1648. And I think that's it, because all of the other forces here act perpendicular to the ramp, right? So I think that's it. So the net force on my system is going to be the sum of all of these 4 blue forces that I just wrote out, right? So if you add up all of those forces, that net force ends up being negative 17.9254 newtons. And so now we can use that to find the acceleration of the system, by taking that net force and dividing it by the mass of the system. So the mass of the system is just going to be these two masses here added together. And so that gives us, what, 4.95? 4.95 kilograms. So divide it out, and you get an acceleration of negative 3.62 meters per second squared. There we go. All right. So now that we've got that acceleration, in order to find the tension, what we need to do is look at one of the two boxes. Okay. So let's pick a box. It doesn't really matter which box we pick. Let's arbitrarily, I'm going to pick box number 1 for absolutely no reason. All right. So let me free up a little space here. Okay, so what did we say? We decided we were going to look at box 1. So here's box 1. Here's what we know. We know that gravity is pulling box 1 down with a parallel component of negative 8.085 newtons. And we know that our force of friction kinetic on box number 1 is 3.1648 newtons. And we know that the rod is doing something. So there's some tension force from the rod, but we don't know what it is. And in fact, we don't even necessarily know what direction it's going, right? Because it's a rigid rod. So it's possible that the rod could be, I'm going to draw this in green here, the rod could be pushing up the ramp, right? Slowing down its motion. Or, alternatively, it could be pulling down the ramp, speeding up its motion. And I don't know which of those two things is happening yet. Okay? So, I'm going to just leave it as this, and we'll let the math tell us what direction it's going to go in. All right? But there's one other thing that I know. I know that the acceleration of my block is negative 3.62 meters per second squared, which means that I can find the net force. Now remember, this is all block 1. So the net force on block 1 is going to be equal to the mass of block 1 times the acceleration of block 1. Now I do know that both of my blocks have the same acceleration, right? Because they're all tied together. So my whole system has that acceleration, right? So here we go. So the mass of block 1 we had decided was 1.65 kilograms. The acceleration of block 1 is negative 3.62 meters per second squared. So multiply this all out, and you find that the acceleration of block number 1 is, the net force on block number 1 is negative 5.9751, there's a decimal there, meters per second squared. So now what I'm going to do, I'm going to go over here and do a little more work, is this. I know that the net force on block number 1 is equal to the force of gravity on number 1 parallel plus the force of friction kinetic on number 1 plus the force of tension on block number 1. Now notice the force of tension on block number 1 is going to be the same as the force of tension on block number 2, right? So that one there is a little bit redundant. But so let's solve this thing. So you get negative 5.9751, oh no, meters per second squared from that force. Let's try newtons. Newtons equals negative 8.085 plus 3.1648 plus the force of tension, and solve this thing. The force of tension ends up being, it does give you negative 1.05 newtons, okay? Which means that the tension is pulling down the ramp in this example. All right, so there's your answer. All right. Now we could have just as easily done this for block number 2, and we would have gotten the same answer, except that we would have gotten positive, right? Because if block 2 is pulling block 1 down the ramp, then block 1 is pulling block 2 up the ramp. All right. Now here's the kind of neat thing about this. In part C, if you switch the order of the boxes, if you put mass 2 here and mass 1 here, then all of the numbers that are here stay the same, right? And so you still get the same acceleration, right? Which means that this drawing looks exactly the same, right? But what that means is now, instead of the rod sort of being stretched so that the rod is pulling mass 1 down the ramp, it would have to be pushing mass 1 down the ramp, okay? So instead of the rod being in what's called tension, being stretched, it would be being in compression, which means that it's being squished. All right, but the answers are the same. Just changes whether the rod is being squished or not. Right? So the interesting thing to note, though, is if you switched the order like this and replaced the rod with a rope, then the tension would be 0. Is that right? That is right. Yes, because mass 2 would then have a bigger acceleration than mass 1, right? Because there's a smaller coefficient of friction. All right, so that is that.